What we'll do today is continue with our discussion of Chapter 18 on Bayesian learning. And what we did last time is focused on the situation when the parameter set was discrete. And we looked at the setup for Bayesian learning, the notion of a meta-network, and how we can view evidence as data. And how we can condition the meta-network on a data set and then compute posterior distributions over parameter sets that we can then use as a basis for either computing point estimates like map estimates or for doing more Bayesian learning in the sense where we average over all possible parameter sets and their probabilities. So today what we'll do is we'll continue this discussion by focusing on continuous parameter sets. And let me explain what that is. What we did last time was, if you have a parameter set like this, which talks about the distribution over a smoker, whether someone smokes or not, given that they're not health aware, then we said that we only have two values. It could be either this or it could be that. And then we gave probabilities for these things. So this was the prior knowledge. And we kind of, the implicit assumption here is there's no other values. It's only these two, right, for this particular parameter set. But now we'll look at a situation where we will allow every possible value for these guys, right? So any values that add up to 1. And that would be an infinite number of distributions. We will refer to this as a continuous parameter set, which is usually the norm. That's what people assume. And the key thing here that's going to happen is because of this, we can no longer use a CPT to represent our prior knowledge. So a CPT is a table that assigns probabilities to a discrete number of values. Now that we have continuous parameter sets, we need another tool. And generally, you need basically density function. But interestingly enough, for this situation where you're talking about a parameter set, there is one particular density function that's used for this. It's known as the Dirichlet distribution, and that's what we're going to focus on. The Dirichlet is the standard in this particular case, and it's everywhere in terms of equations. Very simple and has nice properties, but we'll need to develop our intuitions about it. So we're talking about this parameter set, let's say, whether someone is health aware or not. So first component is they're health aware, they're not health aware. And let's say that in this case, we expect this parameter set to be this, 75 and 25, right? But we don't want to rule out other values. We want to allow every other possible value, but in a sense, what we want is that our belief in other values will decrease as they deviate from this. So this is kind of the expected value, and as we move further away from it, we want our belief or our prior knowledge to, our belief to be less, our prior belief to be less. So that's what you could use Dirichlet prior for. And one way to look at it, if you look at it from a practical point of view, is that to specify this Dirichlet distribution, what you really need is two numbers in this case. These are the psi h and psi h prime, and they're called the exponents in this case. So the idea here is, if you have these two exponents, then this would be the expected value of this parameter, right? So you take the psi for h and divide it by the sum of the exponents that give you this guy, and then this guy here end up being the expected value of theta h prime. So you just took the exponent for h prime and divided it again by the sum. So let's take a concrete example. Let's say you have this exponent 7.5 for h, and the one for h prime is 2.5. These are the two exponents. So what is the expected value here? 7.5 over 10 and 2.5 over 10. That's this guy. So the expected value in this case is 0.75 and 0.25. Now here's the interesting thing. These two exponents give you that. Now, what if the exponents were 75 and 25? What happens in this particular case? You're going to get the same expected value, right? But there is a difference between the two, as you see in just a little bit. Right? So as far as the expected value, they're the same, but what will happen is the confidence in this expected value will be different for these two cases. If you add up these exponents, as we did here, then you can interpret that number as a measure of confidence in the expectations that they lead to, these exponents. In fact, this sum is called the equivalent sample size of the Dirichlet distribution. Right? If you add up these exponents, where a larger equivalent sample size is interpreted as providing more confidence in the corresponding expectations. One way to look at it is how many individuals I've actually seen, right? So if I give you 75 and 25, you're saying I'm basing this on having seen 75 of this type and 25. So, but if you say 750 and 250, you've seen more, right? So in a way, you're more confident in what's going on, guy. But let's take one more example now where the variable has three values. So initially we use the variable E to mean exercise or not. So assume that it's binary, but let's now assume that it has three values. So it's either E1, which is the individual does not exercise at all, or E2, the individual exercises but not regularly, and then E3, the individual exercises regularly. So it's three of them. So in this case, the parameter set has three values. It's a vector of three components, each one corresponding to one of the particular values of the variable. And if I need to have a Dirichlet prior over that, then I need three exponents, right? One for each. So let's say these are the exponents, 10, 60, and 30. Then in this case, you can see what that would lead to. This is the expected value of the first component, and this is the expected value of the second component, and that's the expected value of the third component, right? Again, 10 plus 60 plus 30 is the equivalent sample size in that particular case. So far, it's basically straightforward. We'll tell you a little bit more about the Dirichlet, but if you want to look at the official definition of this distribution and the underlying PDF, here's the definition. So a Dirichlet distribution for a continuous parameter set is specified by a set of exponents. We're going to assume the exponents are greater than or equal to 1. You can deal with situations where the exponent is between 0 and 1, but that complicates things. For example, it will no longer be unimodal and so on. So we're going to avoid that. We're going to assume that the exponents are greater than or equal to 1. Now, as we said, the equivalent sample size is simply adding up the exponents. So look at the notation here, because it's going to be used next. In this case, psi, look at x. X is the small, so that's a particular value of the variable, right? Given u. And then I'm summing over all possible values of x. Now, what am I writing here? Big X, right? So this is a property of the variable itself, and that's the equivalent sample size, where I'm adding the exponents that correspond to each one of the variables, the values of x, right? So here's the equivalent sample size, and that's what we're adding. Okay, now, by the way, you will not need to remember this. Just for completion here, the Dirichlet distribution has the following density. This is the density. It still has a intuitive form. So look what I'm doing here. I'm talking about the density for a particular parameter set. So remember, what is this? This is a vector, correct? That has different components, one component for each value of the variable x. So what am I doing here? I'm looking at these components, that is the thetas for each particular value, raising it to the corresponding exponent minus 1 and taking the product, right? So it's pretty nice. And then I'm normalizing. There is a normalizing constant there, which is eta, that happens to be this. This is called the gamma function. Okay, you can look up the details. But that's basically what the density looks like. You'll never have to work with this guy, by the way, because this density, the expectation, the variance, the mode, all have simple, nice forms using the exponents. The expected value of a particular parameter or a particular component of the parameter set is this, which is what we did numerically already, right? So the expected value of this parameter, you just look at its own exponents divided by the equivalent sample size. And that's the variance. The variance of this parameter is given by that, right? And look what's going on here. Look below. Equivalent sample size. So as the equivalent sample size goes higher, the variance gets smaller. And that's basically the more confident we have in the expected value of these network parameters. Again, the PDF itself has this maybe more involved form, especially its normalizing constant as we've seen in the previous slide, but that really doesn't end up playing a role in practicing or in using the Dirichlet prior. When you use the Dirichlet prior, you need to just know about the exponents and what is the expected value and the variance, and I'll show you next even there is a nice closed form for the mode. That is, if you look at the space of possible distribution and you want to pick the guy that has the highest density, that's also nicely characterized as you see in the next slide. That's the mode, right? So again, what we're trying to do is find a parameter set that has the highest density, and these are the components. So for this parameter, you just take the exponent minus 1, the sample, equivalent sample size minus this guy. This guy is the number of values for the variable x. So if x has 2 values, then this would be 2. And that's basically what's going on. So nice form for the expected value, nice form for the variance, and then also a simple form for the mode, right? And now you're going to see how these come together and give you all of these parallels to what we did last time. Last time we did a bunch of equations for the posterior, for the Bayesian estimate, for this and that, for the discrete case. Now we're going to see the same things, but for the continuous case where the prior and the posterior are Dirichlets, and actually in a way they're going to look even simpler as you see in just a little bit. Let me just make one more comment here. When you have two exponents, that is when you're talking about binary variables, the Dirichlet is known as the beta distribution. People may have heard of the beta distribution and not of the Dirichlet. So this is a special case when you have two exponents. Yes, you had a question. How do we find the exponents? Okay, now you're starting a fight between the Bayesian guys and the non-Bayesian. So this is considered to be prior knowledge. You inject it as an expert. And that's one of the main arguments between this approach and the Chapter 17 approach, maximum likelihood, that doesn't use this. And the philosophical argument here is, where do you get this from? And the non-Bayesian will tell you should only look at data and nothing else but data. And here you will have to inject this one way or another. Together with data, right? Because what you have is they have the meta-network. You use these exponents or the CPTs to put prior knowledge on parameters, and then you have data as evidence. And then you compute the posterior. So you're getting both. Your posterior over the parameters is being based on two pieces of information, data and prior knowledge. And you'll see in a little bit, we can show you situations where if the prior knowledge has certain properties, it washes out. And then you end up relying mostly on data. So we'll tie the two together. But that question you just asked is the philosophical distinction between the two approaches, right? Some people tell you, no, this is, once you start putting priors, you're messing things up. It's subjective, and you should only rely on the data and nothing else. Good point, good question. Okay, so from this point of view, actually, let me take this opportunity to say, when you say Bayesian, that's a very overloaded term. In the hardcore community, when you say Bayesian, that means this. Are you okay with priors or not? So say I'm Bayesian, I'm not Bayesian. But then in AI, Bayesian, when people transferred from logic to probability, and they talk about Bayesian reasoning and so on, Bayesian meant just probabilistic. So there is a lighter and a heavier use of the term Bayesian, right? And again, in some cases when you say I'm a Bayesian, it says I'm okay with priors. I'm not a Bayesian, I don't go with priors, just likelihood. That's one sense. But again, the other sense is just using probabilistic reasoning. So when we said Bayesian networks, we didn't commit to this heavier use of the term Bayesian. We're talking about Bayes rules and so on. So you gotta be careful with what people mean with Bayesian. What I'm gonna do next is just a few quick slides on the use of continuous parameter sets, because if you look at it, if you're using a Bayesian network like this guy, and these are continuous variables, then this creature is something that we haven't talked about yet, right? We talked only about networks where every variable is discrete. So you're gonna tell me, what does this mean? You're going to see it's almost the same. So I'm going to flash a few slides just to make you feel comfortable. None of this really is going to play any role in manipulations you need to do, just to give you a sense that the semantics and similar things just carry over, but you'd have to be working with a combination of densities and distributions. And then once I do this, then I'll go back and give you the equations, because now we have the Dirichlet, then we're going to see how we're going to use it to do the posteriors, the Bayesian, and so on. So look at this guy here. These three variables are discrete, H, S, and E. And then we have these three variables that are continuous, right? These are the parameter sets. And now, when everything was discrete, we talked about the distribution over these variables. Now we have to talk about the density of this network. And it's going to look like this. So by the way, I don't know if you realize, you're using rho for density as opposed to PR or the big P. So look what we have here. We have the 5 variables. 3 of them are discrete and 3 are continuous. And the semantics are the same. We have basically the chain rule. These root guys are just these densities. And then I have H given this guy. And then I have S given this and that. Same thing. The only difference is, now that I have these discrete variables, that's a probability. And for these guys, it's a density, right? And the whole thing in this case is the density. Now, as we know, when we were doing, when we wanted to sum out variables, discrete variables, we do a summation like this. So if you have an expression like this, and you want to sum out these guys, you just do a summation over all possible values of H, S, and E. Now, if you do that, what do you get? You get a density over the other guys, right? That's when we sum out discrete variables. What happens when you sum out continuous variables? You integrate, right? So here's the same density over all 6 variables, and I'm integrating over these parameter sets. This is a shorthand for successively integrating over every component of that. So we're just going to write it briefly like this. And then what do you get? You get a probability in this case. Distribution over H, S, and E. Again, you will not need to manipulate any of these things, just to give you a sense of what's going on. And here's yet another example. What I'm doing here is first summing out all of the discrete variables from this guy. And then I'm integrating out 2 parameter sets. And then I'm left with the density over this particular guy. Right? Straightforward. And look what happens here. These are the 2 famous equations from last time, where we showed that parameter sets are independent a priori in a meta-network. Same thing here, right? Except you're talking about the density. The density decomposes into this. And if you remember what we said last time was the posterior on parameters also decomposes when the data set is complete, right? So we wrote the version of that, and same thing here, except that we're talking about the density. The posterior density over this decomposes into 3 posterior densities, where we take the product of these. So anyways, you see the parallels of that, and the same thing for conditioning. You basically, everything applies. Here's our first equation, which parallels what we did last time. So we just have a few of them. Recall what that is. The main result, or the main concept we did in Bayesian learning, was that if you're interested in the probability of some alpha, and you have some data set, D. So what you do is you will say, well, I don't know what the parameters are. Let's say they're theta. Let's plug the theta in the Bayes network and compute the property of alpha. And then in this case, I'm averaging over, or I'm integrating over all possible thetas and then weighing by the density or the posterior density of that theta given. So we've seen a version of this where this was a sum over all possible thetas, and this was a probability. So that just generalizes to the case of density like this, right? This is what we talked about as the main quantity that one would want to compute when doing Bayesian learning without having to commit to a particular estimate. And if you remember, when we looked at the meta network, the n slices of that meta network hosted the data set. But if we wanted to do this, we said we could add one more slice, n plus 1, and compute the probability of alpha on that given data, which is asserted on the first n slices. Same thing, right? This is one of the observations we did last time. It still holds in this case, except that this is an integration instead of summation. Here's also another parallel to what we did last time, which is the Bayesian estimate. Remember what the Bayesian estimate is? You have the posterior or the prior on some parameter set, and you're computing the expected value. So in this case, this is the posterior density, and same story like last time. I'm trying to compute the expected value for this guy. I integrate over all possible values of this parameter set, and for each one of them, I pull the component and multiply it by the density, again, straight forward. And this is the main thing from last time, which still applies in this case. If I'm trying to compute this guy, where effectively I'm averaging over all possible parameter sets, I really don't have to do the averaging. If I manage to get the Bayesian estimates, I plug them into Bayes network and just do the computation and get the same results. Everything stays the same, but this is under complete data. Okay, you have to realize some of the equations we looked at applies more generally, but this particular case where the fact that the Bayesian estimates, which are point estimates, will allow you to have the same effect as averaging, that happens when the data set is complete. So pretty much everything is the same. So what's missing in this picture is what? What's missing in this picture is, now we're talking about specific density. We're talking about the Dirichlet as the prior. And then if you condition on data, complete data, the posterior will also be a Dirichlet. So if you want to implement this thing, I want to tell you, if you start with a meta-network where your priors are Dirichlets, which are specified by these exponents, then what happens when you condition on a complete data set? Now, in general, by the way, if you start with the priors that belong to a certain family, let's say Dirichlet, and then you have a data set and you condition on it and compute posteriors, there is no guarantee in general that the posteriors will belong to the same family, that the posterior distribution will also be Dirichlet. There's no guarantee in general. But in this case, if you start with Dirichlet priors and your data set is complete, and you condition, the posteriors are also Dirichlet, then if I want to tell you how to compute the posteriors, what do I have to tell you? One thing, how to compute the new exponents, correct? Because the Dirichlet is just specified by a set of exponents. And that's what we're going to do next. It turns out to be a very simple formula. So what is going to happen is the following. Starting with a meta-network with priors that are Dirichlets that are specified by exponents, and given a specific complete data set, given that you condition on it, I'm going to tell you what are the new exponents. Once you have the new exponents, use the formulas to get the mode, to get the Bayesian estimates, all of that. Going to be very simple, and you're going to see it next. And that's really what you're going to take home is those things that are coming up, because that's what will allow you to implement all of this. By the way, that's what we're going to do next, and then we will use the opportunity to contrast the results we're going to get with maximum likelihood, where we don't have nice observations. And then we'll do a little bit about what you do when the data is incomplete, And that's going to be it for this chapter. There is a lot more material. I'll just mention it briefly at the end, but we'll not go over it. All right, folks. So here's one of the nice things about the Dirichlet. If you have a meta-network where each parameter set has a prior Dirichlet density that's specified by these exponents, right? One for each value of the variable. Then, given a complete data set, the posterior density on a particular parameter is then also a Dirichlet density that's specified by the following exponents. These are the new exponents. Look at this. What's going on here? That is the prior exponent. And I'm telling you what would be the new exponent, the posterior. And it turns out to be just the prior plus this. What is that? You guys recall what this notation means? Go to your data set and count how many examples have this particular variable instantiation XU. That's it. And I have to tell you, this you need to know, and it will probably be on the final. That is, I give you, there will be a question on Dirichlet. So I'll give you Dirichlet, and I say, here's the exponents, here's the prior, here's the data set, and what is the posterior. It's just so important and simple. All right, let's take a concrete example. Here's a parameter set, and in this particular case, it's a binary variable, so there's two components. One for smoker, given that they're health aware, the other not smoker, given they're health aware. And we have a prior Dirichlet density, which is specified by these two exponents, right? Those two numbers, that's it. They specify the Dirichlet prior. Now, clearly then the expected value here is what? 0.1, 0.9 for this guy. Now, here's the data set. I have this data set. It has 5 examples. It's a complete data set. Look at H, S, and E. They're all fully specified. The posterior density is also Dirichlet according to our previous result, and it's specified by the following exponents. What do I do here? SH, if you look at the prior, that was 1, and then I add how many times did I see SH in the data set. Actually, if you look here, true, none of them. So that's a 0. So that stays at 1. And in this particular case, the posterior exponent is 9, which is the prior, plus how many times did I see S prime H? So if you look here, S prime H, or basically true false, that appears twice. Number 2 and number 3, correct? 2 and 3. So you add 2 and that's 11. So I had initially 1 and 9. Now I have 1 and 11. And basically the expected value of the posterior is 1 over 12 then, and 11 over 12. It's pretty straightforward and nice. Now look what happens now. The ultimate reward now is, now that the posterior has the simple form, then you can talk about the Bayesian estimates of the posterior, right? Which is just the expected values. You can also talk about the mode, the parameter set that has the highest density, and that allows you to do map estimates. When doing Bayesian learning, I'm computing posteriors over the parameter sets. If you go and pick up the parameter set that has the highest probability or density, then you're doing map estimates, right? You're finding the estimates that have the highest probability. If you're computing the expected values, then you can use these to do the averaging and so on. Let's look at these formulas next. And this will allow us to contrast them to the maximum likelihood. Okay, pay attention here. These 3 equations tell you a lot. If you compute the expectation of the posterior, right? We saw before that if you have a Dirichlet with certain components, the expected value has a simple form. You just do the same thing except that you plug in the posteriors, and that's what's happening. Okay, look at this part. Forget about this here. Look at this. This was the case for the prior, right? The expected value of x given u is you just take the exponent divided by the equivalent sample size. Now I'm doing the same but for the posterior. The posterior, the exponent becomes this guy. I add this component, correct? And if you take this quantity and sum it up for all possible values of x, you get this guy. So So again, I've added this. So this is what got added when I'm looking at the posterior. This here was the prior, and given a complete data set, now this is the posterior, or the expected value of the posterior. So this is now the Bayesian estimate given this complete data set. Okay, stare at it. There was also a formula, if you go back to the previous slides, that told you if you had a Dirichlet with the following exponents, then this is the mode. This is the parameter set that has the highest density. If you take that formula and plug in it the updated exponents given a data set, you get this. That's basically the guy that has the highest density or posterior density. It's almost the same as this, but you have these guys here. Okay. Now we're going to contrast this with one more thing. You guys remember in chapter 17, we talked about maximum likelihood estimates. Do you remember the formula? The maximum likelihood estimates, empirical probability, which was what? It's this. You counted how many times XU appeared divided by how many times, okay, and this was that. These were the maximum likelihood estimates under complete data from chapter 17. So now I want you to look at this guy, right? And this guy, which does the map, and this guy, which does the Bayesian. We're going to make now a number of observations that help you see the difference between them. One observation is what we talked about before, that these maximum likelihood estimates suffer from what people call the problem of zero counts. That is, you may look in your data set and you may find that this parent instantiation doesn't appear anywhere. So this is a 0, then this is not defined. And if you recall when we mentioned this last time, we said when you do the Bayesian approach, that problem doesn't surface. Look why. Let's go back to these equations. When this is 0, you will still be okay. And similar here. What's happening here? In a sense, we are falling back on prior knowledge. Right? The data is not telling me anything about that. I'm not seeing that instance, but then prior knowledge kicks in and helps with that. The other thing that the observation is, again, look at this. This is the maximum likelihood that is not using priors. This is just pure data. These two are using priors. What happens as the data set grows or tends to infinity? What happens? These counts will start dominating, right? And these things converge towards the ML estimates, the maximum likelihood estimates. So in a sense, this prior knowledge kicks in more when you don't have enough data. But as you have more data, then it starts washing out and becomes less relevant. Okay, there's one more thing to say about this, to tie them together. In fact, if you remember in the discrete case, we showed that when the CPTs on the parameter estimates were uniform, the two guys, map and maximum likelihood, ended up being the same. You have a version of this here. So people will say that a Dirichlet distribution is non-informative if all exponents are equal to 1. All exponents are equal to 1. What happens in this case? The expected value of a parameter is just 1 over its cardinality, right? So if you had a binary variable, that's be half and half. A variable that has 3 values, 1/3, 1/3, 1/3. That would be the expected parameter set. Now, under this non-informative prior, look what happens to the Bayesian estimates. You just plug in the exponents, you get this. And look what happens to map estimates in this case. What are these? These are the maximum likelihood estimates. So they end up basically corresponding to each other in this particular case. When you have non-informative priors, in a way you washed out your prior knowledge, and then you're relying mostly on data in this particular case. If you want to summarize these 3 estimates under complete data, maximum likelihood estimates tells you find me the parameters that maximize the probability of the data. Map estimates says find me the parameter estimates that have the highest probability given the data I've seen. So one is probability of theta given d, the other is probability of d given theta. They end up being the same if you do not have some bias on a priori on what theta should be. But they are different if you do have prior knowledge on what the theta might be. These are these two guys. They are point estimates. The other way of doing it is to say I don't want to commit either to maximum likelihood or to map, but I want to average over all possible values of the parameters and weigh by their probability. That's kind of the core Bayesian approach. And in some cases, doing that is the same as finding Bayesian estimates, which are unique, point estimates, and plugging them in. That's basically the summary of what's going on in this situation. I want to give you an example of what you can do when the data is incomplete. Right? So in this chapter, again, what's coming next is what happens when your data is incomplete. This is all complete data. There are several methods for dealing with incomplete data. I'll just give you one. And then the last part of the chapter talks about structured learning when you're doing the Bayesian approach. So you have a more general notion of a meta-network where you start integrating the possibilities of various structures. That gets a little bit hairy, and the results are somewhat weaker. So you have to make assumption after assumption after assumption to simplify the math and eventually get something that you can use. So we'll not do that. But you should be able to read it given what you already know. So what we will conclude here with this chapter and the subject of Bayesian learning is, again, one example of what you could do when the data set is incomplete. And what we'll end up doing is something that we have seen a version of before. I will show you a version of an EM algorithm that tries to compute the map estimates. Okay, so the idea behind map estimates is, remember, map estimates is you're looking at the posterior and you're trying to find the estimates that have the highest density. Okay. If your data is large, then the idea is the distributions start being really focused on the map estimates. And the map estimates can be viewed as an approximation of the Bayesian estimates. That is, if you were to average over all possibilities versus just look at the map, they start coming closer towards each other. So a lot of people will tell you that computing map estimates is in a way an approximation of averaging. And that approximation becomes better as your data set grows. Right? So that's why there has been focus on computing map estimates. So this is what we're going to do. What we're going to do is, assuming that you have a meta-network with the Dirichlet priors and your data set is incomplete, then we'll show you a method that tries to compute the map estimates. It's going to be an EM in the version that it will guess some parameters, right? And then it will do iterations, and in every iteration, it will improve them. That's what we're after. We're after the posterior density on the parameter sets given a data set in a meta-network. The point here, though, is this data set is now not complete. So some variables do not have values. And the notation here is D with this superscript of C. The idea is that this is a completion of that. What does that mean? This is a partial variable instantiation, correct? So if you have, let's say, 3 slices, this guy's saying on slice 1, I know these variables. In slice 2, I know these. In slice 3, I know these. Because it's incomplete, it doesn't fix the value of every variable in every slice. Think of this as one way of filling the unknown variables. So there are multiple ways of this, right? So if in the first slice, there's 2 variables missing, then I can complete them in 4 different ways, and so on. So I'm summing over all possible completions of that data set. Okay, this is straightforward here. If you just, do the summation of this and apply Bayes' rule, you get basically the following. Look at this guy now. What's interesting here is the following. What's happening here? The posterior on theta, given what now? D and its completion. So this, I'm conditioning on a complete data set. That we know how to do. Right? That's the posterior density, given a complete data set, has a nice form. What is this? The probability of a completion. We've seen that before, right? Okay. So basically what happens is, I'm trying to optimize this guy, and the insights that we've seen from EM before is that, let me try instead to optimize the following. Look what's happening here. Instead of optimizing the posterior density, I'm going to optimize the following, the expected. What's happening here is, I'm looking at theta, but under an incomplete data set D, and I'm trying to complete it using the previous parameter estimate, theta sub k. So that's what's going on. Again, I'm not going to go into detail of this. We've seen a version of this before. This is the posterior under a complete data set, and this is the completion, right? Using this guy, computing the expected or the probability of this completion under the previous value of parameter estimates. Okay, so again, it turns out that if you optimize this guy, then you can never worsen the estimates. That's the guarantee that's here. If you try to find this parameter estimates at k+1 that optimize that guy, then look what you get, the guarantee. The density over this could not be worse than that. It's either the same or better. That gives you this algorithm which says, okay, start with your some guess of the estimates, and go ahead and optimize, find the new estimates by optimizing this quantity, then you have improved their density. Now that you have these guys, do another iteration, and you keep iterating. So what are you doing every iteration? You're either staying the same or getting a better density, same kind of stopping condition. So the only thing that's missing here is, how do I actually optimize this? If you give me your current parameter estimates, theta k, how do I get theta k+1? Right? And what we're doing here is, again, trying to optimize this. And you can see the math in the book. It turns out to be simple, nice form. If you had theta k and you're trying to optimize that, the parameter estimate at k+1 that have that property are these guys. Okay, almost there. If you stare at this equation, what is this? These are the prior exponents that I know, but I need to compute these. What are these? Expected counts, just like we've seen before in EM. And how do I get these? You look at the Bayes network, you plug in theta k, and you can actually do this computation. So you have to do inference on the Bayes network to do this guy. Okay, and then you can see the pseudocode in your book. Almost parallels what we did for EM in chapter 17, with some of the equations being a little bit different, most notably this guy. Okay, same kind of inputs. You have the Bayes network, you have some initial parameter estimates, you have a data set, but now you have the prior Dirichlet. That's the new difference here. So once more, let's just visualize this before we end. You are trying to find parameter estimates that have the highest density, right? And I will try to do this by guessing some parameter estimates. They have a certain density. And then I use this to do one iteration. And this guarantees you that the new parameter estimates will either have the same density or better, right? If they're better, you do another iteration. At some point you stop. Now you don't, no guarantees that you're going to get a global optimum, right? Just like we've seen before. So it's kind of a best effort thing. And interestingly enough, the amount of work you have to do to perform each one of the steps is similar to what you've seen before. Okay, I mean, there's details, but conceptually very simple and similar concepts. And at least it gives you something to do when dealing with incomplete data and when your prior knowledge is specified using Dirichlet distributions. All right, so what we've done again once more in this chapter is allow you to do learning when you have prior knowledge. We looked at the discrete parameter case, we looked at the continuous parameter case. In the discrete parameter case, the prior knowledge was just simply CPTs over discrete values of the parameter sets. In the continuous case, we had Dirichlet priors, and we saw that in both cases, when the data is complete, things are very well behaved, nice closed forms for the posteriors, and a lot of nice semantics. When you have incomplete data set, it gets a little bit more complex. Again, once more, we didn't cover structured learning in this case, but that's discussed in your book. This is basically all I want to say on this. Starting Thursday, we will do causality. You're going to see a conceptual shift. It will be very, by the way, very intuitive, high level. I'm looking forward to the next lecture.